Electricity, potential, work, and energy. Questions to ponder. How is electrical potential related to work? What is potential difference and voltage? What work is required to move a charge? How are potential difference and kinetic energy related? What is the relationship between electric fields and potentials? And what are equipotential lines? So let's start off by talking about potential and work and the relationship between those two. So here's our system. We have a positive charge here, and then we have a test charge right here. The potential out here at location R1 is given by our potential equation here, which is equal to K times Q over R. So you can see as the distance gets further and further here away from Q, the potential dies down and follows this curve. So to understand the amount of work that would be necessary for me to move this charge closer and closer to Q here, we have this equation. As you can see, if we didn't start here, if we started with Q, positive Q way out here, understanding that these positive charges would repel, it would take work for us to move this charge inward. So we'd be giving this charge energy by moving it in, because if we let it go, it would turn back and run the other way quickly. So we're giving it energy, so it's positive work we're doing when we're moving a positive charge towards another positive charge here. And that amount of work that we're doing when we're moving it closer would be equal to the amount of this charge times the potential here. So if we look at this, we would really have KQQ over R. And if you remember Coulomb's law, KQQ over R squared is the amount of force here. So if we had force times that distance, you can kind of see how it would relate to work. Because again, if this was Coulomb's law, this would be KQQ over R squared. We would, multiplying by that distance R, we would get rid of one of the R's, and so it would equate. So it doesn't work out exactly that way, but the bottom line is, in our electrical system here, as we get these charges closer and closer together, the potential is getting greater and greater, and we're doing more and more work. So this is an equation you definitely want to memorize. Work is equal to the charge times the potential at the location of where that charge is. Now we're going to see if you can already use this in a problem. So here's our problem, and it's a pretty easy one based on the equation you just learned. If a 2 nanocoulomb charge has a potential of 12 volts, how much work was required to move it to this location? So give this problem a try, and when you're done, come on back to the video and see how you did. So, how did you do? We have a 2 nanocoulomb charge with a potential of 12 volts. So the work is the charge times the potential. So 2 nanocoulombs is the same thing as 2 times 10 to the negative 9 coulombs times 12 volts. And that ends up being 2.4 times 10 to the negative 8 joules. And that's how you can calculate the work in our electrical system here. Now we have a concept of potential difference and energy. To understand the idea of potential difference here, it's quite simply the difference in potential. So if we have a charged plate on this side that's positively charged, and we have another charged plate over here which is negatively charged, then there's a difference in potential between these charged plates. And just like if you have an object with mechanical potential energy, where you had an object that you lifted up a certain height in a gravitational field, we have an electrical field here that's uniform between these two plates. And just like with gravity, we could choose our reference point at any location. So if we choose our reference point as this side of as this plate right here, and we call that potential at this location 0, then this would be 20 volts of potential over here relative to this location over here. So we would have our charge that if we moved it up here over close, and of course positive and positive is going to repel, and as we were moving it, it was moving away from the negative, which was attracting it. So we were doing work to move this charge from zero potential up to this potential of 20 volts. So the work that we did to move that charge from point A to point B is equal to the amount of charge here on this object and multiplied by that potential difference between point A and point B. That being the work that we did, what we did when we moved this charge is we gave that charge some potential energy. We changed its potential energy from 0 up to its new level here by doing work. Notice, therefore, the change of potential energy, just like when you lift a rock, you're changing its potential energy by the amount of work that you do. The change of potential energy is equal to the charge multiplied by the potential difference when we moved it. And if we release this charge and let it go, it would go zooming back over to this side, and it would zoom back and release all that potential energy. So the amount of kinetic energy that it would gain as it moved across would be equal to the potential energy. So this kind of a system is just like a mechanical system where we lift a rock and do work and give it potential energy, and then we let it fall, and all that potential energy turns back into kinetic energy. So the kinetic energy that the charged object would have here would be equal to 1/2 mv squared, and so and all of that would be equivalent to the original work that we did, Q times the potential difference. So finally, if we did let this charged object fly and let it go, we could solve for the speed that it would have by multiplying both sides by 2, and then dividing both sides by m, and then taking the square root. So this is our equation that we get for the speed of this charged object that would be hurled if we let it go within this uniform electric field here that when it has this much potential difference. And we have one other idea here, and that is if we have a potential difference from one point to another, that potential difference is also called voltage. And I'm sure you've heard of voltage before, so I forgot to mention that earlier. When we talk about potential difference, sometimes we also will just simply talk about voltage. And of course, voltage is measured in volts. So we have a problem here about a speedy electron. What is the change in potential energy of an electron? And the electron has a charge of 1.6 times 10 to the negative 19 coulombs. An electron also has a mass of 9.1 times 10 to the negative 31 kilograms. So that electron, what is the potential energy of the electron being accelerated in a uniform electric field with a voltage of 5,000 volts? And then if it is let go, how fast will it be going after it is fired through the charged plates? So here we did work, gave it some potential energy we're going to calculate at this point, and we're going to let it go, and it's going to come flying through these plates, and we want to know how fast it'll be going. So give this problem a try and come back to the video when you are done. So how did you do here? The first thing we needed to find out is what is the change in potential energy when we do work to get this electron over by this negative plate here. And so that's equal to the charge on the electron times the potential difference. So we take the charge of an electron, 1.6 times 10 to the negative 19 coulombs, and multiply by 5,000 volts, and we get negative 8 times 10 to the negative 16 joules. And that doesn't seem like very much energy, but of course we're talking about a mass of an electron that we're going to be accelerating here. So the next question is how fast it will be going. So we use our speed equation that we got from the kinetic energy being equivalent to our charge times potential difference. And when we plug into that, we have 2 times the charge on the electron times 5,000 volts, and then divided by the electron's mass. Then we need to take the square root, and after doing all that, we find out that this electron is going to be traveling at an incredible speed of 4.2 times 10 to the 7th meters per second. So we can get that electron moving very, very fast. That's 6 zeros after the 2. This is a what's called a cathode ray tube, and you can see here that we have one end connected to this power supply to a positive potential, and the other end connected to the negative potential of this high voltage power supply. So this is very much like the problem you just did, where we had one we had a potential difference from one side to the other with a high voltage, 5,000 volts, and then electrons will be fired across or released and fired across from what's called the cathode to the anode, and they'll move across a very fast speed, and you'll be able to see the beam because they have a screen in here, a phosphorus screen, that will illuminate the electron beam. Our next idea to talk about is the electric field between charged plates. If we have these same two charged plates with a potential difference of 20 volts across them, then we can calculate the electric field strength between them. This is a uniform electric field, and so the electric field strength is equal to the potential difference and the distance between those relative locations that create that potential difference. So in this particular example, since our potential difference is 20 volts and the plate separation is 5 centimeters or 0.05 meters, the electric field strength from one side to the other here would be equal to 400 volts per meter. That's how you could calculate the electric field between charged plates. We also have equipotential lines that are perpendicular to these electric field lines here, and the equipotential lines show the potential at different locations. Since our zero potential level was at this side, as we move across here and increase the distance, the potential increases linearly with distance until we get to our 20 volt level. So from here to here, that would be a potential of 5 volts relative to our zero location, and then we'd have a potential of 10 volts midway, 15 volts 3/4 of the way, and 20 volts all the way over. And one last thing I forgot to mention earlier is that the electric field strength anywhere between these two charge plates is uniform. Before we calculated the potential difference across the whole plates, a separation of 0.05 meters away, and our potential difference was 20 volts, and we got 400 volts per meter. We can see here that if we were midway, we'd have a potential difference of 10 volts, but our distance here for the potential difference would be 0.025 meters, and so we would still have an electric field strength of 400 volts per meter. So the electric field strength is the same anywhere between these two plates. So hopefully you can answer these questions now. How is electrical potential related to work? What is potential difference and voltage? What work is required to move a charge? How are potential difference and kinetic energy related? What is the relationship between electric fields and potentials? And what are equipotential lines? So, Scratch's parting idea. And hopefully you keep working on your continuous improvement.